This is a tutorial for tutorial 3A on graphing techniques, question 3. Question 3 tells us that the curve C has the equation y equals to x plus k over x minus 1, x plus 2, where k is a constant. It asks us to obtain the equations of the asymptotes for C. So when we look at this graph, the first thing that we should notice is that this is a rational function. What does a rational function mean? Well, it means that you've got one polynomial, which in this case is x plus k, divided by another polynomial, x minus 1 times x plus 2. In this case, if I want to find my horizontal asymptote, all I have to do is set the denominator equals to 0 and solve. So when does x minus 1 times x plus 2 equal to 0? Well, it does so in two places. The first is when x equals to 1, and the second is when x equals to negative 2. So these are our two horizontal asymptotes. What about sorry, not horizontal, what am I talking about? These are our two vertical asymptotes, sorry. My apologies. So these are our two vertical asymptotes. What about our horizontal asymptote, or is there even a horizontal asymptote? Well, what we recognize is that if we expanded out this bottom line, we'd get x squared plus x minus 2. And I don't really care about exactly what it is. What I care about is it's an x squared on the bottom line. On the top line, I only have x to the power of 1. So when x becomes very, 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 very large, say a billion or a trillion, then this would be like a trillion on the top line. A trillion plus k. K is still, it's just a constant, right? It's not that big. And then on the bottom line, I'd get a trillion squared. So a trillion divided by a trillion squared, that's 1 over a trillion. That's a tiny, tiny number. So what we see is that as x becomes very, very big, the x squared, this becomes closer and closer to x over x squared, and that becomes closer and closer to 0. So we get a horizontal asymptote. It's getting closer and closer to the line y equals to 0. So that's the first part. The second part tells us to find the range of values for k for which C has two stationary points. So again, we'll just recall that our equation was y is equal to x plus k over x minus 1, x plus 2. Right? Right, so the range of values of k for which C has two stationary points. Well, what do I know about stationary points? I know that for a stationary point, the derivative should equal to 0. So what is the derivative of x plus k over x minus 1, x plus 2? It's slightly easier if I write it x plus k divided by x squared plus x minus 2. This will just help me with my differentiation. So this is quotient rule, so the whole thing, top line is going to be the derivative of x plus k, which is 1, times the bottom line, which is x squared plus x minus 2, minus the derivative of the bottom line, which is 2x plus 1, times the top line, holding it constant. And this will be over the bottom line squared, x squared plus x minus 2, whole thing, come on, whole thing squared. And I'm going to set that equal to 0 for stationary points. Right, come on. So I'm going to solve this equation now in x. Well, I'm not going to solve it per se, actually. What am I going to do? Well, okay, first thing I'm going to get rid of this denominator, multiply both sides by x squared plus x minus 2 whole thing squared. It disappears because I'm multiplying the right-hand side by 0. And so I get x squared plus x minus 2 minus, and expand this one out, 2x squared plus 2kx plus x plus k. And that's going to equal to 0. Well, this now is a quadratic equation, but I know more than the fact that it's quadratic. I want to find the values of k for which it has two stationary points, i.e., I want to find the values of k for which this equation has two real roots. So we can use what we learned in Chapter 1, dealing with discriminants, to find the range of values of k for which this equation will have two real roots. So let's simplify it a little bit. We get minus x squared minus 2x squared. You have x minus 2kx minus x, so it's just going to be minus 2kx minus 2 minus k. So minus 2 minus k equals to 0. And again, just for my own sanity, I don't like minus signs, so I'm going to just write this as x squared plus 2kx plus 2 plus k equals to 0. Two real roots, two stationary points, means two real roots. So therefore, my discriminant, b squared take 4ac, should be bigger than 0. So in other words, I should have 2k squared take 4 times 1 times 2 plus k, should be bigger than 0. So what does that give me? That gives me 4k squared minus 8 minus 4k should be bigger than 0. I'm going to get rid of the 4. This becomes a 2. So I get k squared minus k minus 2. I know how to factorize that. This is k minus 2, k plus 1 is bigger than 0. So if we use our number line method, we know that this is a parabola, and we know because k is positive, it's going to be a happy parabola with roots at -1 and 2. And I want the values that make it positive, so I'm looking for these values and these values. So my answer is therefore k is less than -1 or k is bigger than 2. And so that's my answer for part 2. Part 3. Sketch C for the case where k is equal to -2, giving the exact coordinates of the turning points and the axial intercepts. So firstly, again, remember we were dealing with y is equal to x plus k over x minus 1, x plus 2. So this means that now I'm dealing with the equation y is equal to x minus 2 over x minus 1. Sorry, that's a bit ugly. X plus 2. Okay, so what can I find out about this? Well, again, I know my asymptotes already. So my asymptotes I've already worked out in part 1. They're going to be x equals to 1, x equals to -2, and y equals to 0. What about my axial intercepts? So first one, let's look at the y-intercept. So for the y-intercept, I'm just going to set x equals to 0, which means y will be 0 minus 2 over minus 1 times 2. That's just going to be 1, right? -2 over -2. So that means I've got a y-intercept at 0, 1. What about my x-intercept? Set y equal to 0. If y is equal to 0, then I don't need to care about the bottom line. Just look at the top line. I'm going to get x equals to 2, because if the top line is 0, the whole thing is going to be 0. And so that means that I've got a x-intercept at the point 2, 0. I have to give the exact coordinates of the turning point, so I can't just draw the graph and hope for the best. So my turning points well, what did I find the derivative to be? If we look up, we can see that I found the derivative. Oh, hold on, where's it all gone? Good. The derivative was negative x squared minus 2kx minus 2 over minus k, over this whole thing squared. So we're going to, too far, dy by dx is equal to negative x squared minus 2kx minus 2 minus k over x squared plus x minus 2, whole thing squared. We set this equal to 0 for our turning points. And what do we find? Well, again, the bottom line is going to cancel itself out when we cross multiply. So again, oh gosh, I've made a bit of a hash here, sorry. I know what k is now. So I could write here plus 4. And I could write here plus 2. So this is quite nice. This is the equation. So the bottom line multiplies up. I've just got a minus 2 plus 2 cancels off. Negative x squared plus 4x. This is just x 4 minus x equals to 0. So that means that I've got turning points when x equals to 0 and when x equals to 4. Now when x equals to 0, y equals to 1. I've worked that out. That means that my y-intercept is also a turning point. What about when x equals to 4? Well, when x equals to 4, y equals to 4 minus 2 over 4 minus 1, 4 plus 2. So that's going to be 2 divided by 3 times 6. That's going to be 1 over 9. So our turning points are going to be 0, 1, and 4, 1 over 9. So now it comes time to draw the graph. So we'll come down here and just remember all the things that we said. So we have asymptotes at x equals to, oh, what happened there? Asymptotes at x equals to 1. X equals to minus 2. Sorry, I'm trying to do this without a ruler, so mine's not going to be horribly neat. I will expect, of course, you guys to do better with yours, but you'll be able to get the gist of it from this. We have intercepts at 0, 1 and 2, 0. And we've got a turning point at 4, 1 over 9. And I should also label my axes, and I'll label my curve, y equals to x minus 2 over x minus 1, x plus 2. What does this curve actually look like? Well, we need our GC to help us when it comes to drawing this. We sketch it on the GC, we see what we get. The way it should look is something like this. And I realized I left off one of my asymptotes, y equals to 0. So please note that there's always this asymptotic behavior. As I get close to the asymptotes, I should always get closer and closer. I never flick away, so don't do something like that, okay? And I never end up going parallel to it either. I'm always getting closer and closer, okay? So I think that's all I've got time for in this video. I'll do part 4 in the next video.